Hello, everyone. Happy April 1st. I promise you nothing here is April's Fool. I'm so honored to be here. Since I'm talking in SysML, I ignore all of the background about why machine learning or deep learning is important and why we have so many frameworks, machine learning frameworks in the recent years. Instead, I'll focus about what's common characteristics of all of these systems. So all of these modern machine learning systems are designed for iterative workload, where you define one step and you do it over and over and over again to optimize a certain set of parameters. And also because of the popularity of deep learning, the design principle in developing these frameworks is we are dealing with the compute-intensive workloads, and using some kind of accelerator, SIMD accelerator, is a first-class citizen in these systems. And lastly, these systems are designed for rapid experimentation. As a result, the default representation of the workload in this system is a DAG, where nodes are a predefined ops, hiding the difficulty of coding for GPU or TPU or whatever you may have, and make them portable. And also, there is much emphasis on how would you speed up this process so a researcher get to the next round of refining their model or their result. So it has been long gone. The time that deep learning could be a state-of-the-art deep learning model could be trained on a single machine has been gone, and distributed training is a normal in any AI pipeline. There are many paradigms you can do the distribution. One, for example, in the data parallel, each worker will have a copy of the model, and the input data, whatever it is, will be divided between all of these workers. And these workers in each iteration tries to synchronize their changes to the parameters and go to the next iteration. So $1 million or $1 billion question is why distribution does not scale? And there has been a lot of works on why this happens. To explain it simply and in an abstract fashion, I'm going to explain it through the DAG structure. So in a simplified baseline deep learning model, we have the forward pass, which reads each parameters individually, and in the backward pass, we update these parameters. And the order of reading and writing is almost reverse. In this picture, I recorded 2 iterations from training ResNet on TensorFlow. The x-axis shows the time, and each of these arrows shows the time when a parameter is being updated in backward pass, and end of the arrow shows when the parameter is being read in the next iteration. As long as machine learning system can synchronize these parameters before the end of the array, we wouldn't have any slowdown on the distributed execution compared to a single machine execution. But if this doesn't happen, we have a slowdown which could potentially limit our scale-out performance. There are generally 2 reasons why we may miss the deadline. The first one is easy. If your network is not fast enough, you cannot deliver the data in a timely fashion. The second reason, which is usually overlooked in the literature, is the order of transfers. You may have a fast enough network, but if you deliver this transfer in the wrong order, you are missing a lot of deadlines, even though you could do better. And since all of these orders are reversed, you get the parameter updates in the reverse order of using them, it's easy to actually miss these deadlines. So let me give you an example. In this simple DAG, each blue rectangle represents a computational op, and the red circles represent a network transfer. So This being a DAG, we can execute it in any topological sort. In one sort, we can start with A, finish the A, and do the B later, and we get the best performance. Or we could start from B, and at the end of the B, we don't have anything to compute, so the computation will be blocked until we finished A. And this computational blockage is really easily observable on the trace of distributed training. So this is an example of training in Inception v3 on TensorFlow with 4 workers and 1 parameter server. And as you can see, we have 2 different types of computation blockage in this timeline. So we either have a bad order of transfer, which blocks us at the beginning of the training, or we are fast enough, or we were lucky enough, but we had to wait for someone else with a bad training at the end. So to fully study this effect and show how different approaches target this problem, we propose this performance model of computation utilization. Deep learning being a compute-intensive workload, we want to use as much computation as we can to speed up things. In this model, we have 2 components. The first component is communication to computation ratio. In one iteration, you have to do a certain transfer, and you have to do a certain computation. And the ratio of this tells you like how well you can do. If you have a lot of communication, you will underutilizing your GPU anyway. And the second component, we call it overlap coefficient. Overlap coefficient shows how well you overlap everything. 0 means that you didn't overlap anything, and you technically sequentially do computation. And 1 means you had a perfect overlap. And clearly, we want to be on the top left of this picture anyway. In the example I showed you, we are roughly here. So we didn't have we had a chance to fully utilize the GPU because we had more computation to do, but because of the blockage, we didn't have the overlap. And the goal of TicTac, the system I'm proposing in this paper, is to move this point to the higher level, to the better overlap. For the comparison, most of the optimizing distributed works focus on network to computation ratio. They either do it by increasing the computational time, mostly by increasing the batch size per worker, or decreasing the communication time by decreasing the number of transfers needed in each step, size of the transfers to extreme of 1 bit, or do a system optimization to make everything faster on the transfer size. There are a few works on the overlapping. Most of this work focus on the cases where best order is trivial, and surprisingly, some of this work get away with applying the worst order possible and still beating the baseline. So in our solution, we make some additional component to the current systems. So in a typical system, we have a base model. We convert this base model to a distributed model, and we send this model to execution engine. In a TicTac, we add 2 more components. We have a component that takes the base model and find the best order of transfers. The best order is represented as a priority list. We give this priority list to an enforcement module, which works with execution engine to enforce this transfer. And we take advantage of iterative nature of this system, so we find the best order offline before the execution started, and we use this priority over and over in this step online. And yeah. So how to find the best order? Finding the best order essentially is a scheduling problem when you have multiple resources on a worker, and this resource is supposed to run a set of operations which have a DAG-like dependencies, and each operation can can be executed only on the certain class of resources. And our goal is to find the minimum make span through the better network transfer priority assignment. This problem specifically is known to be open problem. The simpler version of this problem has been proven to be NP hard, has been shown to be NP hard, and as to the best of our knowledge, there is no approximation with guaranteed boundaries to solve this problem. So we cannot find the optimal one, so we try to approximate one. We took two approaches. In the first approach, we start relaxing the constraint to the degree that it becomes solvable in polynomial time. And to do so, we assume that all of the computation ops takes 0 seconds, essentially removing them from the DAG. And we assume that all of the network transfer only takes a unit time. And by doing this, we could find the best order in this relaxed problem by doing a simple critical path analysis. And in the second approach, we didn't relax anything. We use a simple dynamic list scheduling algorithm. It's dynamic, still on the offline board. And we use a heuristic to find the best one. Go to the paper to see the details. To our surprise, both of these methods work nearly identical, and both of them could achieve empirically the good result. I'll get to it later, but we didn't really differentiate the result because they were identical. The second problem to solve is enforcing the order. So when you request a transfer in this system, you essentially send a request to whoever has this data. In our example, a worker to the parameter server. Parameter server, if has the data, create a response and send it back. One way to enforce the order, one may wonder, is to add the control dependencies to the DAG. And if we do that, we wouldn't need to make any changes to framework, whatever it might be. However, this caused a huge underutilization network because it takes time to send a request to a server over the network and get the result back. And when we did that, the whole point of ordering thing simply vanished because of the underutilized network. The alternative is just to enforce it just before we send a response from the server. The biggest problem is it requires framework modification, but grad students are cheap, so we did it anyway. And one other problem is still we have the underutilized network problem, especially when lower priority transfer is ready to be sent, but it's waiting for higher priority transfer. And there is this small time where we are not using the network. So in summary, this is how the TicTac result look like. On the left side, you see the picture I showed you earlier, where we had gaps either at the beginning or the end. And on the right side, you see how TicTac removed these gaps by doing a better communication ordering. We also experimented beyond like the visualization. So we use Microsoft Azure as our test bed. We tried two different workloads, one training with SGD, and the other one is inferencing using a parameter server, pretty similar to how it's being done in some of the reinforcement learning setups. We tested a number of convolutional neural networks, and to keep the evaluation fair, we use the original per worker batch size reported in the original paper. So the first noticeable result we had is the performance consistency. On the left side, you see the overlap coefficient of execution, or one sample execution. And as you can see, the red dots represent tag, and we are pretty close to the best possible order. On the right side, you see the normalized step time, and as you can see, the variance of tag is much smaller than vanilla TensorFlow. I guess I forget to mention, we tested it on TensorFlow. So in this picture, I show the throughput gain in terms of sample per second of using TAG compared to vanilla TensorFlow. In most cases, we have a performance gain, in some cases significant. And for the simpler models with lower number of parameters, we didn't actually have a significant speed up. In fact, in some cases, we had slowdown because of the network underutilization I mentioned. The other interesting observation we had is, at least in the context of parameter server architecture, increasing the number of workers does not significantly change the gain we are getting, since every worker is independent. One other observation we had, which is obvious here, but I digest it for you here, is as the DAG become more complicated, the number of ops increases, we can clearly see a correlation between performance gain and number of ops. So I'm going to finish this talk with talking about limitation of this work and the future work. So TicTac or any other computational ordering matters if you are in the reasonable realm of network to computation ratio. And the picture I cleverly show you it shows the good region. If you go to the extreme regions, there is not much point in ordering anything because the gain is so minimum, you don't want to add extra overhead. One example is Deep Lab over Summit system. It's the first system ever that break the exaflop barrier a few months ago. And in this system, the ratio is about 5%, and you don't see any benefit of actually doing any ordering. And another example is when you have a huge communication to computation ratio, which basically make your job network bounded instead of compute bounded. So it doesn't really matter if you put any ordering there. So I lied a little bit. There is a third reason you may miss your deadline, and that's network efficiency. Then the machine learning job, especially with parameter server, are a great source of network congestion. And network congestion make you to use less of the bandwidth than that's available to you. And one way to fix this problem is to use RReduce. We compare our system to Horowat with MPI, which specifically try to fix this problem. And interesting observation is, even if MPI, on a non-high performance network, I should say, has almost half the communication cost, it ends up performing worse, specifically because it doesn't do overlapping well. More about it, hopefully, in next SysML. Thank you so much for your attention. I'll take any question you may have.
Thanks, Hadi. Okay, so please come up and ask your questions. Don't be shy. There's 2 mics. I know they're far from you, but we won't look while you walk up. So please come and ask any questions, and we'll just alternate between the mics. Yes, go ahead. Oh, if you could, by the way, just say your name and maybe your affiliation before you ask the question. I think that'll be helpful.
Sure. Mark Tremblay, Microsoft. So it seems like your speed ups are higher for inference than training. Any insight into that?
Sure. The question is why inference gain more throughput, more speed up than full training. One of the reasons is like the overlapping is being done automatically on the backward pass. Like you generate the transfer automatically when you are doing the backward pass. So your gain or your loss because of the overlapping will be amortized by a perfectly overlap part of the training. And depends on your model, you may have between 20% to around 50% of the time allocated to backward pass, and this is exactly what we are seeing on the speed up numbers.
Thanks.
Hi, this is Rick Caillé with Microsoft as well. So it wasn't quite clear to me, maybe you stated it. If network latency were 0, what's the absolute performance improvement you would get over the baseline? I'm just trying to understand, is it 50% overhead, 75%, 200?
Yeah, so latency actually didn't really matter in this work, but it depends on your ratio and number of parameter server. In the best case scenario, you'll get like 50% when your ratio, like network to communication ratio is 1, and you are doing inference, and about half of it when you are doing the full training. However, I should mention it's a free speed up. It's a time you are wasting because of the wrong transfer. It's not like we are compromising something in exchange for this speed up.
Hi, my name is Priya. I'm from Google. So you mentioned the already used case at the end. Do you expect, was that using TicTac, and do you expect TicTac to benefit in those cases?
On the parameter servers, the question is about this picture. So on the parameter side, we use TicTac. That's why it's near 1. On the MPI side, we use vanilla TensorFlow with Horowat, with OpenMPI on Azure.
And do you expect TicTac to help with this if it could work?
So actually, it's a project that we are wrapping up right now. We use TicTac in some part of the project, but we had to come up with a few other algorithms to improve further. One of the biggest problems with MPI is at least in the current implementation, it only happens on the backward pass, and we are not using the 40% time in the forward pass to do any network transfer, and we had to do something about it.
Okay, let's thank the speaker. Thank you, Hadi. Again.
Thank you so much.